Okay. Okay. Good afternoon. Mm, Last time we talked about shared page tables. Additional problems that arise with sharing given memory area, like the program code, arise in processors. For example, we have two students that entered laboratory and they started shell in Linux. Of course, the shell has the same code for two instances of the program. We discussed that this page table should be shared. However, when we run two processes, it's natural that they run or separate processors or cores, whatever. And two processors rise the modified and referenced flags of the pages. It should be done in parallel. It's a hardware problem. We talked about TLB, translation look-aside buffer, where it is placed. Inside the processor to speed up the translation, not to refer to MMU, to get the page number quicker than accessing memory cell or a copy in MMU cache. Okay, but we have two programs or more running on separate processors, so they have the same info on pages in their TLB buffers. It should be synchronized somehow. It should be, for example, when one processor sets the reference flag, it informs MMU about setting the reference flag, and somehow other processors that use the same page index table should be informed about bit R in MMU, because it should be synchronized, the value of this bit. So sharing the raises a number of problems that are not easy to solve. This picture shows some ancient technique for storing pages on the disk. This is typical solution when we have it's not page index table. It is, I think it is misleading. It is table of pages, not table of pages. They are pages simply, pages in memory. They are not in continuous memory. They are distributed over memory because the allocation of frames to pages is arbitrary. So it is misleading somehow. But on a disk, okay, on a disk we have continuous area in which pages of given program are stored. Okay. On the disk, either on disk or in page, which is not true. This picture is misleading in several aspects. Because if we have a page in a table, in a memory, it is on the disk as well. If the page is clean, we need not write it to the disk because it has two copies in memory and on disk. So it is not true that it is an empty. Now, I think that I should redraw a number of Tannenbaum pictures because they do not tell the truth. And if the page is dirty, of course, it has two images in memory and on disk. And the page is written down to memory, to the disk, if we swap this frame that holds this page for another page. This is dynamic page swap. It was used many years ago, this technique, because, oh, it can be used, but I will return to this later. It is for disk or of low capacity. My first IBM machine had 30 megabytes of disk. Probably you have single pictures on your disks that are greater. Then several years after, I bought a disk that had half gigabyte. It was enormous memory space for me. So the operating system should save the disk space, should limit the usage of disk space. And such a technique was used that pages that are in memory are not represented on the disk. Only those that are swap out are represented. So here we see that 6 is only in memory. There is no room for 6. If we swap, we load some page to memory and write some page on the disk. Here in this solution, the clean page must be written to the disk because it has no image on the disk. If we swap out the clean page. When such a solution is used nowadays? In IoT controllers. Especially if they operate on battery, not in continuous power supply. Memory is one of most consuming the power devices in IoT controller. So it's typical that the IoT controller has 32 kilobytes of memory. And for example, 128 kilobytes in flash. In such an environment, if we have paging, it should be organized such a way to save the flash space, which takes the role of the disk. So this solution is used seldom, but you can observe such a solution, especially in memories with very small mass storage. Another aspect is placement of swapping process in operating system. Imagine that we have a user process that runs and it generates a page fault. That means that required page is not in memory. Of course, as every interrupt, it is directed to the kernel. The kernel recognizes that it is page fault and has a special handler. And the role of his handler in that time is only to make up a process. We have a process that waits in a kernel, and in this handler it is resumed, and it returns from previous call to the kernel and starts the swapping algorithm. This is simplified version when we have a free frame. So we do not deallocate some page in swapping mechanism. We just load the page from disk. And when the page arrives, it's the end of the swapping process, and it informs by the kernel call that the page is already in memory, because only the kernel can modify page index tables. So at the end, it calls the kernel. Kernel modifies page index table and informs MMU that the page is in memory, because we can have a copy of page index table inside MMU cache. If we change the position in page index table, and if this table is in MMU cache, we must do the same in cache of MMU. So MMU must be informed. It suggests that this process runs in user space. Typically, it is not true. It runs in operating system, maybe in user mode, but not in user space. This is the system process, quite low in the hierarchy of operating system layers. But this picture stresses that it is done out of kernel, that the kernel only initiates the swapping mechanism, and it is performed outside the kernel. Those sentences are taken from Tannenbaum. We can agree with them or not. It is the truth about the origin of those two mechanisms. Yes, it is true that segmentation was invented to logically separate parts of memory allocated to the program for different purposes. It is true. And that paging is a physical process that allows to use a continuous address space with physical gaps in it. when the pages are not loaded. So the second mechanism is rather to run large programs in small memory. However, using both two mechanisms, we can organize a virtual memory. That means we can use more memory that is physically installed. In paging, we just have some number of pages kept on mass storage. In segmentation, we can use sweeping, which is similar mechanism that sweeps out entire segments to mass memory. So we can run more programs that we can physically fit into memory. Paging is low-level mechanism, yes, invisible to the programmer. Or segmentation is higher-level mechanism, visible to the programmer because the programmer or the compiler should appoint to which segment the reference is issued. Because every segment starts at address 0, not like pages. The page size is constant. Yes, the segment size is arbitrary. Okay. When using both mechanisms, total address space can be greater than available physical memory. True. Segmentation enables better protection of individual elements. I will written this from Tannenbaum, but for me, we assume that system programmer who creates operating system is not a man, and he knows that some attributes should be assigned to pages that just like to segments. Code the attribute read-only. I don't see any difference. Protection is the same. Segmentation enables easier management of process elements of variable size. Maybe in the past, how the memory in Windows is organized. A process gets the entire memory of the computer. It is strange. However, it does not get the entire memory. It gets the entire address space of the computer. And the code, oh, well, we learned, I showed you that typically the memory area of the program is organized in static data, stack that grows towards static data, and heap that grows upwards. So if we exhaust this area, we can ask for more area and the heap is enlarged. Okay, but if we have enormous address space, what is address space in Intel machines? You don't know? 2 to the power of 52. It is address space in Intel machines. So we have the code of the program here. For example, the stack here, the grows downwards, heap grows upwards, but they are just small slices. much smaller that I depicted, because it should be readable for you. In fact, I should give such small areas. So address space of a process is generally empty. Physical addresses allocated to the program are small size of the entire address space. We map other elements to this space, DLLs, files mapped to memory, and many others. So, excuse me, is it easy or hard to organize such an address space? We can reserve gigabytes for a stack of address space, not of physical memory. If the process wants more, we will add frames to the program that will keep those new pages. No problem. So, for me, those sentences from Tannenbaum are highly problematic. And I generally do not agree with them. Easier management. Maybe in the past. But having such techniques and large physical memory and much, much larger address space coming to trillions of trillions, I don't know, 2 to the power of 52. 50 bits is million, 30 is billion, 40 is trillion, so 50 is quadrillion. And 2 bits more, 4 quadrillions of bytes. I don't think that there is such memory for the world. Segmentation enables code sharing between processes. Paging, we learned about interrupt on write. It enables the same. So for me, those sentences are highly problematic. Because paging is transparent and lower level mechanism, nowadays segmentation is used seldom. From modern processors, you can ARM has no segmentation. RISC-V has no segmentation. In Power, you can turn on segmentation on demand, so people don't do it. The only processor that uses consequently segmentation is Intel and similar processors, clones of Intel. Why? Because of backward compatibility to run old programs that are segmented. So it is used in large number of processors over the world. We know that Intel is one of the largest, has one of the largest market share of processors. However, it is for compatibility reasons. Goal of paging: obtain more address. I don't understand this sentence. Maybe I copied this segment with an error to obtain more. Yes, the goal of paging was to run more programs that fit in memory. Nowadays, the goal of segmentation is the same. However, initially, the idea was to separate areas of different type. Separate code, separate data, and split data to some sub areas of given properties. Yes, it was. In segmentation, external fragmentation may occur, of course, because segmentation is connected with dynamic allocation. So it leads to external fragmentation. Paging, when we allocate number of pages, last page may be not fully used, may be used partially. So it's internal fragmentation. This is example of joining segmentation with paging. It is from Multics system. The segment descriptor has some fields. The address of page table, every segment has its own page index table. And the address of page index table is a counterpart of a datum register, which shows where the data are in memory. Segment length in pages is the counterpart of limit register. So if we generate address that in page number has a value greater than this value, memory overrun fault is raised. Additionally, we have interesting property, those pages sizes. Small pages or large pages. A page can have 1024 words or 64 words. A segment can be paged or not paged. We can allocate a continuous area of memory and not page it. It's possible in this system. Here we have protection bits, we know them. Code, read-only. And miscellaneous bits are nothing more than reference bits. How the address is elaborated if we have paging connected with, merged with segmentation. Table of segment descriptors. It is from Multics. This solution is from Multics. This is a table of segments, and segments are of different lengths. So every segment descriptor is like a page, a segment size field. And every segment descriptor has the address of each page index table that stores the addresses of the frames for pages. of course, the pages are of fixed size. In Multics, we learn about number of segments as a part of the address. So address has three parts. We will discuss it later. Segment number, page number, and offset. It is different in Intel. We have no segment number in address. Segment number is guessed by the processor. We have 6 segment registers in Intel. They are called code segment, CS, stack segment, SS, data segment, DS, and additional segments, ES, FS, and GS. We cannot address those last 3 areas without special technique. They are inaccessible. To code, how we refer to code? If the instruction is loaded to instruction register, the processor assumes that code segment should be used because it is instruction is a part of code. If we refer to stack pointer or frame pointer, it's natural that it is stack segment because the stack is in stack segment. Frame pointer points current frame of currently executed function, and stack pointer indicates the top of the stack. So the processor is stack segment. Otherwise, if it is no code, no stack, it is data segment. And those additional 3 segments, ES, FS, and GS, we can access using placing special prefix. We must precede the instruction in memory with the prefix called segment override that specifies to which process the next instruction will refer. It overrides ordinary referring to. It is highly complicated. I think that it's not a good idea. But we have what we have. So the segment number in Intel is deduced. So we see that this picture is somewhere similar to what we saw already. It was multi-level page index tables. Do you recall? Multi-level page index tables. The picture was quite similar. The only difference is that instead of page index table of first level, we have segment table that contains information of segments of various sizes. This is the address in Multics. We have 18 bits of segment number. Of course, nobody uses such a number of segments, 2 to the power of 18. 5, 7, not 2 to the power of 18. 2 to the power of 18 is 250,000. Then we have page number, 6 bits, and offset, 10 bits. So together the address inside the segment is 16 bits. In this computer, the memory was word addressed, not byte addressed. So we have 2 to the power of 16 memory cells. 64 kilo words. Of course, it is in large pages, where when the pages have 1 kilo word, because 10 bits we have here. In small pages, the proportion was opposite, 10 bits for page number and 6 bits for offset. And the addressing was performed such a way that the highest part of the address is segment number. We look at segment descriptor table and we look where the page index table of this segment begins. And we take this, the page index table for this segment. We take the upper part of the address in segment, this upper part of the address in segment, and it is the index in page index table, which contains the address, the number of frame, which is converted to the address by concatenating with the offset, which specifies the word inside a page. This is example of TLB in Multics. We know it. It is page number, but page number we must know from which segment is the page. So segment together with page are the key in associative memory. Frame number is the result. And additionally, we have protection, attributes. We have age, because if the record has 0 in used column, we can take it. If all have 1s, we take one that is most old. It is simplified. What is lacking in this table? Please tell me. Reference bits. This is it has nothing to do with paging. It's a separate topic. It is construction of protection levels in Intel. Intel designed the protection not in 2 levels. Typically, it's 2 levels in other processors: system mode and user mode. From system mode, we can access everything. For user mode, only what is assigned to the program. They designed the processor to have 4 protection levels. The rule is the same. From any level, we have access to this level data, and all with lower priorities. So this is designed for the kernel, this for the rest of operating system, file system management, device drivers, and so on, here. Shared libraries, also called runtime systems, middleware, generally middleware, and user programs. The idea was quite good, but nobody uses this mechanism. The operating system authors use only 0 level and 3 level. This is for operating system, this is for user programs. Those 2 are not used. So we cannot say how it is efficient, because nobody applied this protection model. Later, they invented level -1. Intel is nervous if people say -1, because it shows that the construction was not overthought enough. So the negative level they added. So they did not call it -1 level. But people call it -1 level because it is more privileged than 0. It is for hypervisors. It lets run the guest operating system kernel in 0 mode, because the hypervisor that is more privileged is in -1 level. Is more privileged than any operating system that runs on this processor. Oh, that's all for this slide set. And we switch to the next topic, that is input-output. Okay, first, just to recall the structure of interrupt handler. Not the handler. Handler is a fragment of code. It is interrupt controller. In model solution, the instruction cycle is performed such a way that we fetch the instruction from memory, decode it, execute what this instruction instructs the processor to do. We finish instruction cycle, and before we start executing the next instruction, we look at the interrupt line. If it is in active state, we perform a call with trace to interrupt handler. The address of interrupt handler we take from the table of handlers that is typically in lowest memory at address 0. And we start serving the interrupt, handling the interrupt. When we finish, we send some instruction to interrupt controller that we finished. It is typically writing to a port or on given address. In Intel, it is in PC, not in PC, it is address 40. Write to port 40 is end of interrupt. So this model is called precise interrupt. Why precise? Because interrupts come to the processor in strictly defined moments in time. Between instructions, one instruction is finished, program counter is updated and appoints the next instruction in the stream. Or in the case of jump, it is covered with the jump address. All data are elaborated in the instruction, are stored in registers or set to memory. Everything is clear. That's why those interrupts are called precise. However, do we use precise processors nowadays? Some people, yes. For example, if you build an IoT controller on 8051 Intel processor, it operates just like that. However, typical calculation processors are pipelined. Or most of them are superscalars. In Intel, modern Intel processors, we have 5 pipelines of 20 instructions each. So 100 instructions are in progress in any time of program execution. We never are in situation between instructions. We always have a number of instructions on the way. So such interrupts are called imprecise. So what we can do to serve the interrupt? What do you think? One of methods is convert imprecise interrupt to precise one. Just to hold the pipeline. Not exactly hold. Special circuitry look at instructions in pipeline. Some of them are on late stages of execution. For example, they prepared new values that are only not stored to registers or memory, but the calculation is done. Some of them prepared data for ALU, for arithmetic logic unit. Some of them are in process of preparing those data for ALU. For example, loading data from memory. And maybe some of them are in very beginning, in decoding phase, when we look what to do in this instruction. And this circuit decides which instructions to finish, because they are in a very advanced stage of calculation. So the data calculated are ready, only they are not stored where they should be stored. And other that are preparing data or are in decoding phase, just to cancel. They will be executed second time in the future because they did not execute any calculation. This costs some time and effort, and we need to wait until the instructions that are decided to finish will finish. It takes some time. And starting the interrupt handler, we have the clear situation. No instruction is in progress. It's one technique. The second one is, okay. What circuitry that perform the pipeline, what it contains? It contains some combinational logic and number of registers that hold intermediate results. For example, do you know from computer architecture the technique of bypasses? It is a technique, imagine a pipeline. We have instruction that calculates some value and stores in register R5. And the next instruction takes the value of R5. So in the pipe, to have instruction that calculated the value of R5, but did not store it in R5 yet. It is in some special register called pipeline register, because next instruction, the value is known, is calculated. It only did not reach its destination. So we take the value not from R5, but we take it from this register that holds the value that will be stored in R5. It is called a bypass to speed up the pipeline. So those registers and similar hold the state of the pipeline. For example, arguments on input of ALU are prepared to calculation, and so on. We must store all those registers on the stack. The registers that are unknown to the user, the system programmer or user programmer or compiler is not aware about those special registers. They are hidden from programmatic model of the processor. But there is an instruction. It is enough to have a single instruction. Please store pipeline internal registers on the stack. Of course, we must have room on the stack for doing that. But only once. If we have interrupt in interrupt, it is performed on system stack. You recall that context switch is connected with storing the content of the processor and switching to the system stack. And if we serve the interrupts in cascading mode, it is done on system stack, and system programmer takes care to have enough room on system stack to accommodate all data from the processor that are in program model and that are out of program model. They are state of the pipeline. It is quite large number of data. Recall, Intel has 5 pipelines of 20 stages each. Okay. Here we have a history. Maybe it would be better to have animation. How the cooperation of CPU with external device is performed using interrupts. Maybe separate picture should be prepared for non-DMA input-output. It differs because every data in non-interrupt cooperation comes through processor. Processor at least 2 instructions. In write, read data from memory and write it to the device port. In reading is read from device port to processor register and store to memory. So it's comparing with DMA is extremely slow. However, let us look at DMA controlled device operation. First step is to program DMA controller. We must inform DMA controller about the address in memory of the buffer, the address on disk to which we will write or from which we will read, size of transmission, typically in sectors of the disk, and direction, reading or writing. when we send all those data to DMA controller, it starts to control the disk controller. In this case, it is reading from the disk. And this controller reads byte by byte from the disk to internal buffer and then sends data to memory. When it finishes, or in some error occurs during transmission, the acknowledgement or signal on error is sent to DMA controller. DMA controller knows that the operation is finished and sends an interrupt. It is shown that it sends an interrupt to CPU. It is false because it sends it to interrupt controller. And interrupt controller sends interrupt signal processor. The simplified version. DMA controller has higher priority than the processor. And usually it stops the processor for some time, for the entire transmission, or periodically for some number of instructions. Why? In first solutions, or in generally, the computer bus is arranged such a way that modules compete for access to the bus, sending request signals to the bus arbiter, and bus arbiter decides which module will get access and gives the access to this module for one access cycle. It occurred too slow for DMA. So very old solutions were based on this principle. Next solutions stop the processor for the time of transmission. We will discuss it in detail later. And the processor, after the transmission, will be woken up. So when we work with DMA, we have only one interrupt per large transmission. If we would transfer byte by byte, there will be thousands of interrupts to serve. And every interrupt is connected with context switch. So it would be extremely slow. So everything is done by DMA controller. The time scheme of this process is that we have a process that performs some input-output. It calls operating system. Operating system starts the device. When the device finishes, it sends an interrupt. It wakes up operating system, or operating system wakes up the process. It sends the next byte, and so on and so on. Such a way of doing is, for example, in keyboard, we have one interrupt per character, mouse operation, and similar devices. With DMA, the process that initiates the transmission calls operating system. Operating system here programs DMA channel. DMA channel starts to transmit bytes and issues the hold signal to the processor. Every modern processor has a hold input signal on which we can stop the processor. Not entirely stop, because it can happen that processor fills instruction cache and data cache with instructions and data, and it can perform some calculations quite a long time. For example, some loop can operate on data, and we can execute this loop without accessing memory.
Yes.
But on first access to memory, the processor should be stopped.
Yes.
Because it's not actual stopping, it's prohibiting the processor from accessing memory. Because DMA accesses memory. We can say that it is brutal method because memory is needed for DMA only for small periods of time. And more advanced solutions are, for example, cycle stealing.
What of the spaghetti packed?
DMA channel uses the hold signal, but stops the processor only for several instructions. When it accesses memory, it is called cycle stealing. Some clever solution was used in Motorola processors. I think nowadays such a technique cannot be used because processors are much more faster than memory. Here we see the processor. This is single processor cycle. And in every cycle, processor can access memory. And before or after that, it has some internal switching without accessing memory. Some transfers between registers or whatever. When DMA starts, the clocking device knows about that and matches the length of processor cycle to the time of 2 consecutive memory accesses. One for processor and one for DMA. Such a way, they do not disturb each other. They run in parallel at the cost of slightly enlarging the timer of processor. Why it's not used? Because access time to memory is much more than single cycle of processor. Processors are now extremely fast.
Yes. Okay.
Oh, someone is talking.
I think that somebody can do it. I think that somebody can collect it for you, but I'm not sure, but confirm.
Are you talking to me?
Okay.
Please mute your microphone. Please mute your microphone.
Okay. Nice. Let's see how it goes. But probably they should be able to collect it for you. But let's see how it goes.
Okay. Uh, there are instructions specially designed for input-output. Typically, their mnemonic names are in and out. They operate on separate address space. Input-output ports is typically separate address space from primary memory. And the cells of this memory are called ports. And we have instructions in and out. They are illegal in user mode. So if we use in or out in user program, it causes an error interrupt and the program is closed. It can be used, they can be used inside device driver, which run in system. However, in some solutions, for example, IoT, we have only one application. So we need not protect application from other application or application from them. We can allow the program to operate on devices physically. For this purpose, we have another technique called memory mapped I/O. We program those registers are mapped, those ports are mapped to the primary memory area, so we can access them as any memory cells. The compilers used for IoT have possibility to give fixed address for a variable. For example, we assign the address A0B hexadecimal, which is the address of the port, to variable. We write variable K. Physically, we write to this port of the device. It's much quicker and more efficient and easier for system programmer to do that. But it requires special arrangement of memory. This is the typical distinction of memory and ports. How it is done? We have a special signal from the processor, additional address bit. So if we say that we have 45 address lines, we have 64. If we have 64 address lines, in fact, we have 65. Additional bit distinguishes between memory and I/O ports. And of course, memory is much larger, so the addresses in ports are typically much shorter. For example, 12 or 16 bits. And in-out operations operate on ports because they rise this address bit, those instructions. They rise this bit that selects ports. in the second technique, memory mapped I/O, a part of memory address space is reserved for ports of the devices. So we use those ports just using ordinary memory-aware instructions of processor. We need not use in and out instruction. This picture shows the I/O arrangement in very old computers. I copied this picture from IBM 370 that was produced in the 70s of last century. So it was about 50 years ago. It was during my studies. We have a system bus, CPU, memory, devices connected to CPU directly to the bus, and channels. Selector channels for fast devices like disks or tapes, and how they were used, multiplexer channels. Multiplexer channels switch between devices, allowing to transfer single bytes between system bus and devices, like keyboard, mouse, printer. Selector channel, they are called such a way because they select a device, for example, a disk, and they transfer large portions of data to CPU or memory and disk. Surprisingly, modern computers are close to this scheme because, for example, USB channels are that they act like multiplexer channels. DMA acts like selector channels. Those channels were much more intelligent than nowadays. It was possible to order from the controller to copy entire file on the disk without intervention of the CPU. However, it needed to split operating system activities to processor programs and channel programs, because those channels were in fact processors. They were called peripheral processors. And it was done differently on every computer. So with this organization, we cannot build a system-independent operating system like Windows or Linux, because it was performed differently on IBM machines, on CDC machines, on Honeywell machines. So nowadays, those channels, DMA channels, are much simpler, and they just operate like prepare the transmission, the address in memory, address on the device, number of bytes, and the direction, and it is done similar on every computer. But the general scheme nowadays is similar to those old computers. The devices have some specific values. they differ in arrangement of data. For example, I don't know if you use CD or DVD drives. The way of cooperating with those devices is different, because if we copy files to the device, they are not copied physically. They are copied to the buffer in operating system, in fact on the disk. And when we select burn, the structure is physically burnt out on CD or DVD-ROM. How we can erase a file from CD? CD is written in sessions, and it prepares a directory structure in the section. So, to erase a file, we should prepare a new directory structure and prepare a new session, and this new session does not contain this file that we erase. But of course, there are programs that can access the elder sessions. So we can access the file that is cancelled, but using some system programs, of course, not in user mode. So devices have some specifics, and the role of operating system is to unify. We have files on flash ROMs entered to the disk, on floppy disks. You don't use floppy disk, but think that you saw a floppy disk. DVD, optical disk, mechanical disks, CCD disks. We see the same structure on every of devices. Do you think that the operation and internal structure of every those devices is identical? Definitely not. But the role of operating system is to not to disturb the user, is to give the user a unified view of all devices of similar type. There is printer type of device, so it treats all printers almost the same manner. All the mass storage, like disks, CDs, flash disks, and so on, and screen, it's separate type of device, and remote devices seen through the network. So we have many individual properties of devices, but the role of operating system is split them into some classes and treat them almost equally. What operating system hides some difference between devices, treating them for external world equally or almost equally, but operating system can add some non-existent features to the devices. The transmission between computer and device is, of course, primary service of the operating system, but it's not limited to this. It hides device-specific features. It adds virtual features to the devices. Sometimes a device cannot perform some services, and the operating system helps to perform those services. Access to the device in logical manner, not in physical. We don't write to disk saying, please write data from sector 15 to sector 20. We provide the name of the file, and the operating system knows what to do to find the location of this file, to enlarge it, to write data. Buffering. Especially in Unix-like system, there is a special layer of buffers. So we can desynchronize processes with devices. We can accommodate large amount of data, for example, from disk in the buffer. So the access later is much faster because we have already those data in memory. It's buffering. Tracking the status of device. When we have a printer physically connected to the computer, we withdraw the paper from the printer, and the icon of the printer changes. It is great with some maybe exclamation mark, and when we put the mouse pointer on this icon, it says paper low. It's because operating system takes not only interrupts on finishing the transmissions, but such a device sends interrupts on every status change. If it disconnects, if it's paper low, if it's toner low, if it's laser printer, or ink low in case of ink printer. All those events cause interrupts, and operating system reacts to them, and somehow it changes the shape of the icon. Sometimes it does additional activities. And finally, optimizing access to the device. Performing operations one after another is not always optimal. Sometimes we can rearrange the order of operations that are maybe some operations are slowed down, but at this cost, we achieve lowering average access time, which is profitable for everyone, not for everyone, but for statistic user. Okay, we will discuss all those elements in the lecture. Do we have time? Oh, just the introduction. We have three ways of programming external devices. Non-interrupt maintenance. When we talk about the tracking of what happens to the device, device status tracking, it is not only on base of interrupts. Sometimes the operating system tests the device from time to time, asks about some properties actively. And this is the way of operating in polling mode. We check the status of the device each time we want to learn the status without interrupts. Of course, it's time consuming. It requires some active loop. But this mode is used especially in IoT. When we don't want context switches, because every interrupt is a context switch. So we operate the device in no interrupt mode. We actively test the readiness of devices. And thanks to that, we do not perform context switches. The second mode is interrupt driven in character mode. I will prepare a slide that an animation similar to that on DMA, how this input-output is performed. And finally, using DMA, 3 modes of cooperating with external devices. Okay, that's all for today. Thank you, and see you next week.
I texted you yesterday. You said that you put somewhere the marks for those who